Welcome to the Foundry by Forge College. I'm absolutely thrilled to have you here for this explainer. Now, if you were with us for our last lesson, Foundations of Decentralization, you'll remember we literally took a metaphorical sledgehammer and smashed the central server. We decentralized. But, well, that leaves us with a pretty massive cliffhanger, doesn't it? Because how on earth do we actually engineer trust when there is absolutely no boss in charge?
So, here's the blueprint for today's explainer. 1. The decentralized trust puzzle. 2. Incentives, payoffs, and penalties. 3. Reputation, bounded social signals. 4. Coordination, the commit-reveal trick. 5. DAOs, mercenaries versus contributors. And finally, 6. 3 principles of trust.
Section 1. The decentralized trust puzzle.
Right, so that is the million-dollar question. Without a boss, who actually stops bad behavior? You know, in everyday life, trust feels like an emotion. You trust your best friend, or you trust your local barista not to put like salt in your latte. But in Web3, trust is definitely not a feeling. It's a mechanical output generated by really carefully tuned system design. If the system is engineered correctly, you don't need to know or even like the person on the other end of the transaction. You just have to trust the mechanics.
Moving on to Section 2, Incentives, Payoffs, and Penalties.
Think of these parameters like a schematic for, say, a massive video game simulation. By adjusting the literal math of rewards and penalties, you directly change whether participants are going to choose to cooperate or cheat. So you have a cooperation baseline. That's for when strangers first meet. You've got reputation influence, which binds your history to your future. And then, of course, you have the classic carrot and stick, the reward magnitude and the penalty magnitude.
And you can tune these dials to engineer completely different environments. Like if you want a system that leans really heavily on carrots, you design it so that self-reinforcing cooperation just happens naturally, because the rewards drastically outweigh the penalties. It's a super forgiving system. But if you want to use sticks, you apply asymmetric penalty multipliers, which basically means one single bad move mathematically destroys any potential profit. It creates an incredibly harsh deterrence.
All right. Section 3. Reputation, bounded social signals.
Now, reputation has a massive weak spot. Imagine a high school popularity contest, right? But instead of trying to win people over naturally, you just build 1,000 robotic clones of yourself and program all of them to vote for you as prom king. That, my friends, is a Sybil attack. If creating an identity is cheap or free, reputation is completely fragile. A bad actor can just manufacture an entire army of fake identities to artificially inflate their score and manipulate the whole system.
So, we have to put a lid on it. This is what we call clamping. Practical systems mathematically cap reputation scores. We bound the gauge so that no single user can gain infinite influence no matter how long they've been around or how many good deeds they've done. It kind of mimics how real-world social signals eventually saturate. Like at a certain point, a 5-star review is just a 5-star review, right? You don't magically unlock a 1,000,000-star review.
Section 4. Coordination, the commit-reveal trick.
Okay, here is how you mathematically stop people from cheating in decentralized voting. It's called the commit-reveal protocol. Step 1. Commit. You lock in your hidden vote, combined with a random string of data called a cryptographic salt. You submit this locked box. Step 2. Reveal. Everyone publicly uncovers their vote and their salt. And Step 3. Tally. The system only counts the votes where the revealed data perfectly matches that original locked box. This absolutely stops latecomers from sneaking a peek at the scoreboard and swinging a vote at the very last second.
But this trick introduces the ultimate engineer's dilemma. What happens if someone commits, but then just goes offline and totally refuses to reveal? The system has to make a really hard choice between liveness and safety. Do we prioritize liveness, meaning we just ignore the missing vote and keep the system moving forward? Or do we prioritize safety, pausing everything, because counting an incomplete tally is just way too risky? It's a delicate balance for sure.
Section 5. DAOs, mercenaries versus contributors.
Let's put all this theory into a real-world stress test using a DAO, a decentralized autonomous organization. Here are the actors in our little drama. We've got the contributors. They want long-term value for the protocol. We've got the mercenaries. They just want immediate token capture and quick profits. And we have the observers. They're really just following the crowd based on social signals. The vulnerability here is fascinating, because if those mercenaries successfully manufacture fake reputational signals, like we saw with the robotic Sybil attack, those curious observers will be completely swayed, and the actual contributors will get outvoted by short-term greed.
which leads to an absolute disaster scenario: misplaced incentives. Imagine the DAO decides to reward people with a tiny bit of crypto just for voting, to, encourage participation. Sounds nice, right? Wrong. The mercenaries realize they can profit by voting on absolutely everything, regardless of quality. So the DAO accidentally paid mercenaries to coordinate for short-term profit while the actual contributors completely lose out. In our various Forge College learning programs, we actually spend a lot of time analyzing these exact real-world failures. Why? Because it proves that if you design the wrong incentive, you will efficiently and perfectly engineer your own doom.
So how do we fix it? We apply engineering mitigations. You introduce slashing, meaning voters have to put up collateral, and if they act maliciously, their stake gets mathematically slashed and destroyed. You weight votes by time-locked stakes, forcing people to lock up their tokens for months or even years, which aligns them with the long-term health of the project. And you design reputation decay, so past glory fades if you don't keep actively contributing. Basically, you force them to have real skin in the game.
Section 6. 3 Principles of Trust.
Let's zoom out. To build a system that runs without a boss, you absolutely must do these 3 things. 1. Align payoffs. Make cooperative behavior the most rational, profitable long-term choice. 2. Harden reputation. Ensure that gaining influence is costly and Sybil attacks are economically impossible. 3. Coordinate clearly. Use cryptographic tools like commit reveal to remove ambiguity while balancing liveness and safety. Trust in Web3 isn't just some vague promise. It is an emergent property built by carefully tuning these 3 specific levers.
I want to leave you with this provocative thought as we wrap up today. Look at the platforms, social networks, and apps you use daily. Where do their incentives succeed, and where do they disastrously fail because they're rewarding the exact wrong behavior? Think about it, because once you see the underlying gears, you literally can't unsee them. Thank you so much for joining this explainer. I strongly encourage you to visit forge.college to learn more about this subject and explore other fascinating Web3 topics. Until next time, keep questioning the mechanics.